the vortex tangle around the hotspot in supermassive head.
First of all, I'd like to thank the organizers for giving me such a wonderful chance to give a talk in such a wonderful place. Well, I'm a graduate student with the Professor Makoto Tsuota, and in his talk on Wednesday, he showed these pictures. So I'm very glad that I have a chance I can explain what are these pretty animations. So. First of all, I'd like to explain like why I'm into. Before that, this was animation. So these red things are the heated particles, and these blue lines are the vortex filaments calculated based on vortex filament model. And the motivation of this simulation is, first of all, this situation is very simple and universal. I mean, we can achieve this kind of situation with very simple setup. Like if you have a particle and we just heat it up, and or for example, we have a helium bath and we shine a neutron laser on it, and we can have a very hot region in a very confined place. And this is such a wonderful, such a interesting setup, but it's not yet fully explored until recently. But there are several experiments and numerical studies carried out recently. And also, it's an afterthought, but the simulation actually indicates that this could be a clue to extend the finance equation in a new way, kind of. But let me overlook the experiments and numerical studies. Which is very closely related to this kind of phenomenon. One of these is the observation of peculiar behavior of heated particles in helium-2. One experiment is carried out by Peter Moroshkin et al., and you can find these references here, and also Minowa et al., but this one was the first report of this one was made 2 weeks ago, and it's only available in Japanese for now. But what they basically did was they produced a micron-sized particle by laser ablation in helium-2, and they trapped the particle in the 2D helium surface in the case of Moroshkin et al., and they trapped in 3D by optical trap in case of Minowa et al. And what they observed is the anomalous motion of the trapped particles. And we believe that the anomalous motion was caused by the interaction between vortices and the particle. Because the particle is heated by the means of trapping, it creates a spherical counterflow around it, and it makes the anomalous motions, we believe. And another interesting study is a numerical study carried out by Emil Berger. He did a numerical simulation based on vortex filament model. The same situation, there is a hot spot at the middle and a radial counterflow around it. And he found very interesting results. And the third one is the one just briefly explained by Dr. Weibo just now. So as he explained, in order for better performance of like accelerators and stuff like that, they use helium for cooling for the refrigerator. And the problem is a hot spot is created in the refrigerator, and that limits the performance of refrigerators. And there is a simple simulation I did with vortex filament model. There is a hot spot here, and a hemispherical vortex tangle is created around it. Thank you very much. And let me briefly explain the setup of the computational experiment, which is very simple. There is a bath of superfluid helium-4, and there is a spherical metallic particle in the middle. And this particle is heated by a laser with a constant power. And we assume that there is a very high capital resistance at the surface, at the interface between the particle and the helium. Then that allows us to heat it homogeneously, which basically means we can create a spherical counterflow around it. And what we are interested in is the behavior of vortices near the heater and far away from the heater, I mean the heated particle. And we did two cases of simulations. One is near the sphere, another is far away from the sphere. But let me explain the dynamics of a single vortex near a heat spot first, for the simplicity. So on the left-hand side, there is a vortex ring that moves toward the hot spot. And on the right-hand side, vortex tends to move the other way. On these plots, so this is a distance from the hot sphere to the vortex, and the vertical line represent is the radius of the vortex, and they calculate how they evolve in time. What we see is something like this. So basically what it means is all the vortices move toward the heater, disappear while it travels some distance, while the vortices that oriented the other way can grow in its radius. and some portion just travel outward and disappears in some time. But this calculation is done with local induction approximation, so it doesn't exactly match with the vortex filament model, but it behaves like this. And so let's move on to the detail of the results of the calculations. First, the situation is simple. There is a bath of helium-2 and a solid boundary condition where the particle is. And the boundary condition, so if the particle is like this, and here's a vortex line filament, and because the superflow cannot penetrate the particle, the flow needs to satisfy this boundary condition, which was first discussed by Schwartz in 1985 paper. And on top of that field, there's a counterflow, thermal counterflow field, which is proportional to the heat flux. But there is one problem, that at the very vicinity of this surface, there is definitely layers, very little thin layer where the superflow fluid is converted into normal fluid. So we are not really sure the validity very near the surface, but anyway, we just tried the simulation, look like this. Parameters are like this, which was chosen from the paper so that we can reasonably explain the phenomenon found in here. This is a movie I showed you earlier. So what we see something like a coil-like structure, and something is like swirling around the surface, and it covers entire sphere. And initially there are 6 seed vortices. Out of and 2 vortices are actually trapped onto the surface at the beginning, initially, out of and then let's see the total, how the total vortex lengths evolve in time. It actually turns out that it increases constantly in time. What does it mean? Is that we can understand why it behaves like this in a way, like, so the energy of vortex link per unit length can be calculated by integrating the flow from some lower bound to upper bound, which is like the lower bound should be vortex core size and upper bound is like intervortex separation. It can be given something like this. And since the logarithmic dependence is not that strong, if we ignore this term, we know that the total energy stored in the vortex is proportional to the total length. And because the particle is heated, it's a constant power, the normal, and that energy is carried away by a normal free flux. And the portion of that energy is transferred through mutual friction to the vortex tangle. So this kind of linear behavior can be explained. And let me briefly explain the mechanism of the coil-like structure creation. it seems that small fluctuation or bumps on vortex filament near the heater gets polarized, strongly polarized, and elongated. And they create coil-like structure. And they go to cover up the entire sphere. An intuitive picture of that is something like this. So the vortex filament coils up, and it basically induces the superfluid flow like this, and that tries to cancel out the superfluid induced by the heated particle. So we can think of it as a kind of analogous to Lenz's law in classical ENM. And that creates the thick vortex layer around the heated particle. And this thick vortex layer, actually a few days ago, Dr. Weigo pointed out, it seems to be closely related to the phenomenon reported near a heater. This is a theoretical paper, so it's a computational calculation, but what they are doing is they are creating a pulse of second sound emitted from this heater here. This little thing is a heater. And when there is no vortices, it can propagate almost freely. But when there are vortices, basically the second sound are enclosed in very small region and can't really propagate. After several times, they gradually propagate in a way like a classical Fourier law type transform. So what does it mean? What it means is like, what I want to say is that the strong heat flux can create the thick vortex tangle, and the second sound cannot propagate through the tangle because all the energies are stolen by the tangle. I think my simulation and what they are finding is very similar. They should be closely related. And the second thing, the second case is also there is a path of helium-2. And same as before, we have this thing. But now the particle size is supposed to be very small, so we ignore this thing. But here, what I want to emphasize is that the particle is very smooth, and there is no vortices around it. So we are basically assuming there is no vortex layer we just seen earlier. I'm not sure if this is reasonable assumption or not. This is what we are assuming here, and the result we are seeing is something like this. So basically, the particle size is actually the same size. I mean, the same sized particle is plotted here, but the ratio is, we are seeing very large space, so it looks very small, but the particle size we are choosing here is the same. So let's take a detail. Let's take a look at the detail. So what is happening here? So this is a same animation. Here you have another plot. So this horizontal axis represents the distance from here to here. But the vertical axis represents the size of the vortex. So each black dot represents the vortex ring here. So the animation look like this. So what we can see clearly from this is that we have empty vision here. So it's actually not a bulb, but it's a shell-like structure around the heat spot. And we can actually group the vortices into two types. Here, actually, these the vortices around here help the shell to grow in its radius. And vortices here help to thicken the shell. I mean, the vortices here just goes this way, and each vortex can go up to this line, which is the size of the shell. And for the total vortex length, what we can get looks something like this. So they go and go somewhere like this. So now the question is there any rule that governs the vortex tangle evolution in this kind of situation? Now the problem is the tangle is highly inhomogeneous and localized and polarized because of the heat flux. So apparently there is no equation like Vinen's equation, but it seems there may be a way to explain this time evolution with a Vinen equation-like expression of the form the time derivative of total vortex length and production term and decaying term. Let's see term by term. So the decaying term in Vinen's equation looks like this. Because it's simple, so we have analytic expression which tells this L decays inversely proportional to time. So what if we stop heating the shell? What we get is something like this. So it grows, but it decays in linear. Because this is log-to-log plot, the slope should be the exponent. So we clearly see this kind of decaying behavior. And now the portion around here, this portion looks like we can fit this portion with an exponential function, which means the production term is proportional to this L. So what this indicates is that it's probably reflecting the self-similar structure of the vortex tangle. What I mean by that is, so if I plot the vortex size, vortex ring size versus number at each time, look like a Poisson distribution at the early time of this evolution. So the total number of vortices at some time t can be obtained by integrating this curve. And at time t plus delta t, we have something like this. But basically, it's shifted by r dot dt. This quantity can be calculated from the simulation, and it tells this quantity is the speed at which the tangle shell grows, and it is constant, nearly constant. What it means is that we can expand this term like this. So we have this thing. And here, the total vortex length is the number of vortices multiplied by the average of the vortex length, each vortex ring. And at time t plus delta t, we can write it down like this by taking the leading term, which means we can obtain the relation something like this. So combining these two terms, we can obtain a differential equation something like this. Because this is very simple differential equation, there is an analytic solution which looks like this. And if we try to fit it with this function, it looks pretty good. And we can roughly approximate, we can see the dependence on temperature and relative velocity. But so basically this is, and the conclusion is like, so the behavior of localized and homogeneous vortex tangle is getting attention recently. And we have investigated the process of development of vortex tangle under the spherical counterflow and found interesting properties. I'm not really sure that kind of differential equation can be, binary equation like expression can be valid in any homogeneous cases. But in this particular case, we see something, the behavior something like that. So it's very interesting. And for future work, right now there is no kickback from the normal component to the vortex filament. So I'd like to improve that part. And also, we'd like to see how the vortex layer can affect the behaviors. Thank you.
How do you define the vortex ring size when you actually have a vortex tangle?
Actually,
Curvature radius?
yes, I took a vortex ring and took the average curvature. So sometimes it goes around several values, but average all the curvatures and inverse.
And then in the equation you propose, why there's no diffusion term? You have waxing density gradient. Why not include a diffusion term? Gradient.
Diffusion in the.
I mean, the original binary equation does not have that because it's for uniform system. But now you have non-uniform vortex distribution.
But now this is not the density. I mean, what I'm using here is a total length of the vortex line, not density.
So there's no spatial resolution, no.
But I am not really sure.
Of course, you are right. The other way is to, of course, extend the homogeneous finite integrations to inhomogeneous finite integrations by including the, for example, the diffusion term. Well, this is more reasonable approach.
Have you tried different temperatures?
Different temperatures, yes.
And you always find that the vortex tangle appears?
Well, that depends on which regime we are seeing. Like in the first one, the very near the first simulation, I did calculation near the particle. In that case, if I higher the temperature, I would like less likely well, as Emil Berger's calculation, I'm kind of seeing the similar thing in that region. So higher the temperature, the densities, the tangle is less likely for higher temperature. But lower temperature, the vortex tangle tends to go thicker. But on the other hand, the second, this one, the tendency is opposite. So higher the temperature, we have thicker, longer total vortex length at the end. But the lower temperatures, we have very short total length.
One question. So, is the seeding vortex necessary to see the tangle? The seed vortex.
You see the vortices. Is that necessary to see the tangle?
Yes, because in the vortex filament model, there is no nucleation.
So if there are no other questions, so let's thank us.